All right, welcome back to JICHE. Unlike the annual meeting, we have this one as often as we want. Today I want to talk about a new paper that Ni Zhan, and I have published recently. And it is on uncertainty quantification in machine learning and nonlinear least squares regression models. So you can find the paper in AICHE journal, and I'll have this DOI at the end. So I thought rather than go through the paper, I will just summarize a few points in this slideshow and start out with the problem statement in a nutshell. That is, you have data, you fit it to a model, g of x and theta are some parameters, and that model is nonlinear in theta. And so the model can be anything. It could be the Arrhenius equation, it can be a neural network, it could be the Leonard-Jones potential, etc. And you do some kind of least squares fitting and minimize the sum squared error. And now you want to estimate the uncertainty on predictions for new values. And the whole point of this paper is to introduce or reintroduce the delta method. It's an old idea that allows you to estimate the standard error of the prediction by this equation over here, where this is the gradient of a function with respect to the parameters. This is the inverse Fisher matrix that is related to the Hessian of the objective function you minimized with respect to the parameters. And you just calculate these two gradients in this Hessian and do some matrix multiplication, and that's it at the end. And so the two things we introduce in this paper are, one, this formula, and these are not difficult to calculate for small models, but very tedious for large models. And it turns out there's some tricks with neural nets because the Hessian is often singular, and you need to do some tricks that you can read about in the paper. But I want to just show you how simple it is to implement this. And so in the paper, we have this example here. So this is a Python example with AutoGrad. It's one of my favorite simple automatic differentiation tools. And here we fit a parabola to this data over here on the right. So we define g of theta and x. That function is just this parabola. You could think of it as ax squared plus bx plus c. It's a simple linear model, but this works for nonlinear models too. Then we create a sum squared error function that is going to get minimized. So this is just the sum of our model minus the data squared. We give it an initial guess, calculate the minimum with minimize, and we have the estimate for theta here, and we can make y predictions easily by just calling the original model. Now to get the confidence intervals over here, we use the Hessian function that is available in AutoGrad and just evaluate it at theta. And so that automatically propagates all the derivatives through the objective function and gives us h as a matrix here. And then we invert it with the pseudo-inverse, and we scale it by the sum squared error divided by the number of points, so the mean squared error, if you like. All right, and then over here, we calculate the g prime, so we take the element-wise gradient of our g function with respect to the first parameter, which is theta, so that gives us dg d theta, evaluated at each x point, and then we accumulate the uncertainties as the square root of g prime at p at g prime. So p here is the inverse scaled Hessian or Fisher information. And then we multiply by a t-value, so this just gives us, say, let's see, 0.0975, something like a confidence interval that is given by this parameter. And finally, we have, this is probably 95% confidence, with the two sides being 2.5. And then we make a plot, and you see here these confidence intervals and the fit. All right, and so that's basically it. If you put any other function in here with g, almost nothing else changes after you work it out this one time. All right, so what can we do with this? We can show that if we have some noisy data in blue here and we fit, say, a Leonard-Jones potential to it, then we can see that where we have data, our predictions are pretty reasonable. And as you get away from the data, the prediction error gets high. And that's an indication that you are extrapolating or in a data poor range. That's also true over here where we have this whole gap of missing data here, and the uncertainty in the prediction is larger in this region than it is over here. So qualitatively, that makes sense, and is the way that we're going to talk about that in the next example. In the next example, we show results from a moderately sized neural network. So it has 2 hidden layers with 11 neurons each, 4-dimensional input and a 2-dimensional output. And it's been trained on a data set, I'll just label it 3.9. And then if we train it on data set 3.9, that's a lattice constant for the data, but then try to predict data for lattice constants of 4.0 and 4.1, what you see is the predictions are not very good. They're not bad for 4.0, they're worse for 4.1, and we can see that over here, if you look at the input space, that these don't overlap. So the train is here in yellow, and then the reasonable one is in pink, and the worst one is in blue. So the input space is getting farther and farther away from where it was trained, and that is why it isn't doing a good job. What's interesting over in the right-hand side is you can see that the errors that we estimate from the delta method are kind of roughly related to the errors in the predictions. And so when we see large confidence intervals from the delta method, it's an indication that you need to modify your training and add some of this data back to it. And when we do that, then we get excellent results for both sets of data because we're no longer extrapolating and the machine learning model is acting in a reasonable way. All right, so that brings me to the end. Thanks for listening. That was a brief video summary of our recent paper in AICHE Journal, and I hope you'll find it helpful and easy to use in your own work in estimating uncertainty with nonlinear models. Thanks for listening, and come back next time.